In a compiler, the front end translates source code into an intermediate representation, but the final phase of the back end has a much harder job, mapping that intermediate code directly to a target machine's actual hardware instructions. The code generator operates under brutal constraints. It must preserve the exact semantics of the original program, maximize use of limited CPU registers, and output instructions that execute as fast as physically possible. Mathematically, finding a globally optimal instruction sequence for a generic program represented as a directed acyclic graph is an NP-hard problem. You cannot brute force the answer. With multiple variables and a handful of registers, possible instruction orderings create a massive combinatorial explosion. To make this problem solvable, we have to impose strict boundaries on the input. We restrict our data structure to expression trees and assume a target architecture where all registers are completely interchangeable. Under these exact conditions, we can apply a dynamic programming algorithm. This allows the compiler to find the mathematically perfect instruction sequence in strictly linear time, relying on a behavioral property called contiguous evaluation. By constraining the architecture and data structure, the compiler replaces an NP-hard search with a linear time traversal that evaluates each node exactly once. This diagram shows the abstract syntax tree for the mathematical expression A minus B plus C times D divided by E. If we isolate a generic subtree, we can label its left child T1 and its right child T2. The principle of contiguous evaluation dictates that an optimal program will fully compute whichever subtrees need to be stored in memory first. Then it sequentially evaluates the remaining nodes without breaking flow. A non-contiguous approach does the opposite. By oscillating between instructions in the left branch and the right branch, the processor forces intermediate values into temporary storage, wasting registers and execution efficiency. Since oscillation is unnecessary, the entire tree's cost is simply the combined cost of programs for T1 and T2, plus the instruction at the root. We solve for a subtree once, store its result, and use it as a static building block to calculate the next level up. The algorithm begins with a bottom-up pass. For every node, it calculates a cost vector array, represented as C of I. Assuming a target machine with exactly 2 registers, this array has 3 slots. C0 represents the instruction cost to evaluate the node directly into memory. C1 is the cost to evaluate it using 1 register, and C2 is the cost using 2. We start at the bottom left leaf node, variable A. Since A is already stored in memory, the cost to evaluate it into memory is 0. To load variable A into either 1 or 2 registers requires exactly 1 load instruction. So the final vector for this leaf is 0, 1, 1. Variables B, C, D, and E follow the exact same logic. The algorithm applies this baseline calculation across all remaining leaf nodes instantly. Computing the leaves first provides a constant time foundation. The algorithm moves upward, using these fixed values to recursively calculate the cost of complex operations. We move up the hierarchy to the first interior operator node, the division operation for D divided by E. The algorithm checks every permutation of the child nodes. It compares the cost of leaving the left child in memory and the right in a register against putting both in registers to find the cheapest valid combination. The vector cost for an interior node is always the sum of that optimal child combination, plus the unit cost of the division instruction itself. This logic propagates upward. The compiler sequentially calculates the cost vectors for the multiplication node and then the subtraction node, using the exact same rule. Finally, we reach the root node for the addition operation. Its computed vector contains the absolute minimum cost required to evaluate the entire expression tree, given our 2-register limit. A massive search space of potential instruction orderings has been compressed into a series of simple table lookups. The heavy lifting is finished, and it only took a single bottom-up pass. With the costs mapped, Phase 2 begins. The algorithm executes a top-down traversal, using the completed vectors to trace the specific operational path that yielded that lowest cost at the root. As it moves downward, it permanently tags every subtree. It decides exactly which operations must be evaluated into registers and which must spill to memory to avoid exceeding the hardware limit. This sets up Phase 3, the final traversal required to emit the actual machine code. Following the rule of contiguous evaluation, the algorithm targets the memory-bound subtrees first, ensuring those instructions are the first to be generated. As the traversal hits each node from the bottom up, it emits the corresponding assembly. Load R0 with C, load R1 with D, divide R1 by E. The block is built sequentially. By strictly following the dynamic programming path, the compiler generates the absolute cheapest instruction sequence deterministically, eliminating wasted cycles entirely. The entire pipeline relies on 3 precise passes: bottom-up cost factorization, top-down memory tagging, and a final tree traversal to emit the code. Because the algorithm treats hardware limits as parameters within the cost factor, it can be applied to vastly different machine architectures. Porting the compiler to a new architecture only requires updating the numerical cost of each instruction, while the logic of the 3-pass pipeline remains unchanged. Now, this method does have strict limits. Modern compiler optimizations extract performance by analyzing complex, overlapping data structures. Once a program moves from a strict tree into a generalized graph, this specific linear time efficiency breaks down. Despite its limitations on general graphs, this model remains the foundation of instruction selection theory. It provided a method to generate the provably cheapest instruction sequence for expression trees, a technique canonized in texts like the Dragon Book and implemented in systems like the portable C compiler.